talking about the Galerkin's approach to the finite element method. In this method we basically use the governing equation of the system. Now, the governing equation is typically an equation of the type f of u is equal to 0, okay, where u is the displacement. So, some function of u will be equal to 0. That means, if you are talking of a one dimensional case and if you take a one dimensional element and we write down the equilibrium for this one dimensional element, this would turn out to be delta sigma x by delta x will be equal to 0. Okay, this will get simply by looking at the equilibrium of this. Okay, in fact, if you remember the equilibrium equations we wrote for the general 3 dimensional case, for the 1D case this is a simplified form of that. Okay. So, if we have the governing equation of this type, we can rewrite these governing equations as L of u is equal to P, where P is the load acting on the element at that particular location. So, if we have a general 3 dimensional element like this and we take a element inside this and we write down the equilibrium equation for this, that will typically be of this form, L of u will be equal to P, or we can rewrite it as L of u minus P is equal to 0, okay, where L is some function or some operator upon u. Okay, so, if this is a governing equation, this will form the basis of the Galerkin's approach. This is unlike the Rayleigh-Ritz method in which we are using the potential energy pi. Okay, we are not going to use the potential energy now, but we will use the governing equation, that is the equilibrium equation for the system. So, if you have L of u minus P equal to 0, if you remember in the Rayleigh-Ritz method we had taken some estimate for u, okay, specifically in the example we had considered we had said we will put u equal to a0 plus a1x plus a2x squared. Okay, now this description or this expression for u is not the actual deformation, but is an estimate of the deformation or is an approximation. If we use this approximation in this equation, okay, that means instead of the actual deformation we use the approximation, we will get, let us say, L of u bar. I am saying I am using u bar for the approximation of u. Okay, so, L of u bar minus P, but now this will not be equal to 0, this will be equal to some error term. Okay, L of u minus P is expected to be 0. Okay, but L of u bar minus P, there will be some error term involved in that, because u bar is an approximation, it is not the actual deformation. Okay, so, if L u bar minus P is equal to E, which is the error term, our idea will be, the basic idea of this Galerkin's approach is we will take this error term and integrate it over the volume. Okay, we will carry out what is called a weighted integral. Okay, the weighted integral of this error term, that we will try to put that equal to 0. Okay. So, this error term E, which is referred to as the residual error, and the weighted integral would be, let us say we take some weight E dV and we integrate it over the volume. Okay, and we will try to put this equal to 0. Okay, and here this W is a weighting function or a weight function. So, this W is also a, let us say if this is an object, this W is also a function of, let us say, x, y, z. It is also a field in the 3 dimensional space. Okay, so we will carry out this, the integral of weight times the residual error and integrate that over the volume, and we will try to make that equal to 0. Okay, this is what we will do in the Galerkin's approach, and in fact this is one of the approximate methods where we are trying to minimize the error term. Okay, and what we will say is that this integral, this should be equal to 0 for any weight function that we take. Okay, if we take any arbitrary weight function and this integral turns out to be equal to 0, then we will say that this estimate that we have taken of u bar is an accurate estimate, is an accurate approximation. Okay, that means let us say if I take this weightage to be constant throughout and I get this error to be equal to 0, or if I take this weightage to be some other function and I still get the weighted integral to be 0, which would mean that this E is almost 0, or this u bar is an accurate estimate of u. Okay, so in the Galerkin's approach we will be taking this weightage function w as per a certain norm. Okay, and then we will be taking u bar as per a certain norm, and then we will take w as per a certain norm, and then we will try to get this integral equal to 0. Okay, so let us see the, what is the question?
I am not able to appreciate why after multiplying with the weighting function and integrating over the domain,
Yeah.
and if you make the 0, we say that's a good approximation. Why does this happen?
Okay, let us say ideally if I say that this integral is 0 for any arbitrary w. Okay, this integral is 0 for any arbitrary w, whether w is constant, whether w is varying, whether w is varying linearly or quadratically or in any arbitrary way, and this integral is still 0. When can that happen? That can happen only when E is 0. Okay, so if I can ensure that this integral is 0 for any arbitrary w.
But normally in this method we take particular w, no?
Yeah, so what I am saying is if we can ensure it for any arbitrary w, then I can ensure that E is 0. E is 0 means u is the same as u bar.
That's what I am saying, we don't ensure.
Let me complete. Okay, so what we will do now is instead of taking any arbitrary w, we will take w as per a certain pattern, and we will take u bar also as per a certain pattern, and then we will hypothesize that we will get an accurate estimate of u by ensuring this condition. Okay,
No way we are ensuring that it's 0 for any w.
no,
It's just a better approximation.
There is no way of, in any of these approximate methods, whenever we are doing an approximate method, there is no way of ensuring that the error is always equal to 0.
Just say that u would be better than u bar, what we are supposing.
U bar will be better than the actual estimate of u. Okay, we will go through the process, the steps involved in the Galerkin's approach, and then maybe it will become clearer. Okay, the first step would be that we will say we select a set of basis functions. Let us say we call them GIs. Okay, and just like we did in the last method, we will say u bar is equal to sigma, let us say qi times gi. Okay, if you remember in the previous method we had mentioned that we had written something like u is equal to sigma ai phi I of x y z. Okay, and we said v is equal to another similar term and so on. This is something almost the same. We are taking a set of GIs, a set of functions, and a set of parameters qi, and I am saying that this estimate u bar is equal to sigma qi gi. The GIs are the basis functions which are the same as the phi i's we had in the previous method. Okay, and if you remember the one dimensional example we had taken, we had said u equal to a0 plus a1x plus a2x squared. Okay, this expression is the same as this. So the GIs will be 1 x and x square, and the QIs will be a0, a1 and a2. Okay. So, say u bar is equal to sigma qi times gi, with gi's are the basis functions. Then the next step is to get weightage field or weight field. Okay. And for the weight field we will say that this weight field W will use the same basis functions, that is a restriction in the Galerkin's approach. We will use the same basis functions gi's and we will say, let us say this is sigma some other parameters times gi. Okay. So, if we had, if this was a u over here, then maybe weightage will give it as u is equal to b0 plus b1x plus b2x squared. Okay. So, we will give a weight field which will be given by this. Once you have given it a weight field, then we can find out the weighted error and integrate that. Okay. But on this weight field we give one more constraint. Okay, and that constraint that we give is that this W should satisfy boundary conditions of u. Okay, this is an important constraint in this, or important condition that is attached. Okay, that means W should satisfy the boundary conditions of u. For instance, we said that when we took this u, we said that this should satisfy the boundary conditions that at x equal to 0 u should be 0 and at x equal to 2l u should be 0. Okay. So, in this case we are saying that u bar is equal to this. So, u bar should definitely satisfy the boundary conditions that at x equal to 0 and at x equal to 2l u bar should be 0. Similarly, W, okay, sorry, not u, this should be W. Okay, so this W, the weight field, this should also meet the same conditions. That means at x equal to 0 W should be equal to 0 and at x equal to 2l W should be equal to 0. Okay, so this is an additional constraint that is added in this method. This weightage should also satisfy these boundary conditions. Okay. Then the next step is, now that we have defined the u bar as well as W, the weightage field, we will say that we will find our eventual aim is to find out u bar. Okay, u bar basically means that we have to find out the qi's. Okay, because gi's are the function that we have taken. If we can find out qi's, we found out the deformation field in the body. Okay, so our aim is to find qi. So we will say that we will find qi's such that the weighted integral of W times E is equal to dV over the volume is equal to 0. Okay, or this is the same as W into L of u bar minus P times dV will be equal to 0. Okay, so we will find qi subject to this condition. So this condition will give us a set of equations which we will try to solve so as to get the qi's. Okay. So the Galerkin method will consist of these three steps. First is to select a function or to select a field for u bar, that is to get an estimate or an approximation of the deformation in the body. Then we get a weight field W and then we find out the error and put the weighted integral of the error equal to 0. Okay, and as we put this equal to 0, this set of equations will have some variables in that, those are the Qi's. We will try to get the values of Qi's from this condition. Okay, so this is how the Galerkin's approach works. What I will do is I will take a simple example, the same example as we did last time. We will solve that using the Galerkin's approach, and then I will try to make a general set of equations for a 3-dimensional case. This was the simple example we had taken last time. Now we will take the same example and solve that using this Galerkin's approach. Okay. The first thing is we have to take some approximation for u bar. So let us say we work with the same approximation as we had last time and I will write it directly now. Okay, we had taken a quadratic expression for u. Okay, if you remember what we did last time was that we said that u is equal to a0 plus a1x plus a2x square, and then we said that u at x equal to 0 is 0, so a0 is 0, and u at x equal to 2l is also 0, so we got another condition and we got an expression similar to this. Okay, I think instead of c1 we were using a2 or something like that. Okay, so we will take this expression for u bar. Now if this is a deformation, epsilon we know is equal to del u by del x, and sigma we know is E times epsilon, which is equal to E times del u by del x. Okay, and the governing equation for a 1-dimensional case I just mentioned is del sigma x by del x is equal to 0. Okay, so if I take this as a governing equation, this will become sigma I will replace from here, so del by del x of E del u by del x will be equal to 0. Okay, now since we are talking of a single variable, all the del's can be replaced by d's. Okay, the partial derivatives will become complete derivatives. So this will become d by dx of E du by dx will be equal to 0. Okay, and except for the central point where there is a point load. In the point load we will say that this will be equal to t. We will come to that soon. So this is the governing equation that will be valid for the rest of the body. Okay. Now if we take this u as what we have taken, if u is equal to x into 2l minus x multiplied by c1, then du by dx that will be 2l minus 2x multiplied by c1. Okay, since I have taken this to u to be given this expression, I have to take a weight field, and we said that the weight field will have the same form as this. Okay, if you remember the second step, we said the weight field will be W equal to sigma phi I gi, where gi's will be the same. Okay, and the same boundary conditions will also be satisfied. Okay, so we will take W to be x into 2l minus x multiplied by some other constant d1. Okay, so this is the weight field we will take. Okay, and now we have to evaluate the integral, which is integral of W into E dV, and put that equal to 0. Okay, so this W will get from this expression, okay, or we can put the W into d by dx E du by dx multiplied by dv will be the same as A times dx will be equal to 0, or let us not do that right now. I will just okay, where W is the weight field that we have given. It is going to be slightly mathematical. Okay. Now we want to simplify this volume integral. Typically what we will do is we will make use of the formula that if you have integral of del alpha by del x multiplied by theta times dv. Do you remember the formula for this?
First function into integral of the second.
Alpha times del theta by del x times dv.
Minus
After that
plus
plus the surface integral of n alpha
n dot
alpha theta ds. Okay. So we will be using this integral, and using this we will try to simplify the expression that we have over here. Okay, we have a volume integral which is of the same form. Okay, so if you use this expression over here, your W is the same as theta and this alpha is this expression. Okay, if alpha is this expression, we can simplify it now. We get minus of minus alpha is E du by dx into del theta by del x. Now theta is the same as W, so into dw by dx. Okay, dv I will replace that by A times dx, and we will get the integral of this minus. Okay, this plus this term, this is the surface integral, and this surface integral will be carried out over, if I am talking of a one dimensional object. Okay, my surface is here or here, because the normal is in this direction, and since I am taking a dot with the surface normal, these are two surfaces I have, but in addition to that we have a point load over here. Okay, so if I take into account the point load, I will essentially have to take a discontinuity here to find out this surface integral. Okay, because at this surface I have a normal in this direction, at this surface I have a normal in this direction, plus we have a point load acting in this direction. Okay, if I take all that into account, the normal is either in the x plus x or in the minus x direction. So this you can check up would simplify to W E A du by dx from 0 to L plus W E A du by dx from L to 2L. Okay, you can just verify this. Alpha is the derivative which is the same as E into du by dx. Okay, so E into du by dx is appearing as it is, and theta is nothing but W. So theta and W is appearing in both the expressions. So to evaluate the integral from 0 to 2L, I split it between 0 and L to 2L. Okay, this particular step is slightly mathematical, you can go through it slightly carefully, it will become very simple soon. Okay, so this integral will simplify to this. Now we will try to simplify this integral further. Okay. Now if I take this first term, we will get minus e times a into integral of du by dx. If you look at this term, du by dx is given here, and similarly dw by dx can be found out from here, which is 2l minus 2x multiplied by d1. Okay, so I will put these terms over here, and we will get 4 into L minus x squared into C1 into D1 into dx, x equal to 0 to 2L. Okay, these terms du by dx. Okay, for these terms, if you look at this cross section, at this cross section, this complete term, that is this term, okay, EA into du by dx. What is this? Du by dx is the strain. Strain multiplied by E is the force, sorry, is the stress. Stress multiplied by the area of cross section is the force. Okay, so this term will be equal to P. Okay, so as you evaluate the integral from 0 to L and from L to 2L, at x equal to 0, this term will be equal to 0. Okay, at x equal to L, this term will be equal to P, and at x equal to 2L, this term will again be 0. Okay, so this integral will evaluate to W times P. Okay, where this W is the integral at this point 1. This is my point 1. Okay, so this integral will be W at 1 multiplied by P, and similarly this integral will also be equal to W1 times P. Excuse me. Okay, so this will simplify to minus EA C1 D1 integral of 4 into L minus x whole square dx plus 2 times W1 P.
How is it coming positive in the second case?
Okay, the direction of the normals are different. Okay, as a result of that, a minus sign will come into it. You can do your detailed steps and you will find this out. Okay, the surface normal are in the opposite directions. So if you take care of that, you will get both the terms to be positive. Okay, that is basically because of the discontinuity. Okay, anyway, now this W1, what is the expression for W1? W1 is equal to x into 2L minus x multiplied by D1 at x equal to L. So this will become L into minus L squared D1. Okay, so this term will become minus 2 L squared D1 into W1. Okay, and this term just one sec. Okay, this integral, if you evaluate from 0 to 2L, okay, this will come out to minus E A C1 D1 into 8 by 3 L cube. Okay, in fact, I think there is a minus sign I have got extra. I think you will get a minus sign over here. You can just check it up. Okay, well this term comes out to be plus.
Should this be W1 or P, sir?
Again?
Should this be W1 or P?
W1 or P? Oh, sorry. This would be P. Thanks. Okay, this will 2L square D1 times P. Yeah. Okay. Now this is equal to, if you take 2 D1 L squared as common, we will get P minus 4 EA C1 L by 3. Okay, now this is what the integral of the error term that we have, integral of W into L of U minus P dV is equal to this expression, and we said that we want this term to be equal to 0. Okay, so if I put this term is equal to 0, okay, now this is 2 D1 into L square, where D1 is one parameter that we have, and we have one parameter over here which is C1. Okay, so D1 is a parameter which is specifying the weight, okay, and C1 is a parameter specifying the deformation. Okay, and we want this to be true for all possible values of W. Okay, if this has to be true for all possible values of W, that means it has to be true for all values of D1. Okay, and if this has to be true for all values of D1, then this term has to be equal to 0. Okay, if this term is 0, we can get the value of C1. Okay, so if you put this term equal to 0, we will get C1 to be equal to 3P by 4 EAL, and we have taken U to be equal to X into 2L minus X into C1, that will become equal to 3P by 4 EAL into X into 2L minus X. Okay, so this way we are basically able to get the value of C1. As a result of that, we are able to get a value of the deformation. Okay, what we assumed initially, that we will take a weight field W and we will try to get this integral equal to 0 for all possible weight fields. Okay, that is why this weight field has a parameter D1. So we want this integral to be equal to 0 for all values of D1. If it has to be true, if it has to be 0 for all values of D1, this term has to be equal to 0. Okay, and if this term is equal to 0, we can get a value of C1 from this, and we are thus able to solve for the deformation. Okay, so this is how we can solve for deformation using the Galerkin's method in a one dimensional case. Okay, the steps involved are these: we first select a set of basis functions and make some assumption for U bar. We use the same assumption for W. We ensure that this U bar satisfies the boundary conditions. We also ensure that W should satisfy the boundary conditions. Okay, if this W also satisfies the boundary conditions, then we can go on to the next step, and that is we evaluate the weighted integral, the integral of the weighted error, and we put that equal to 0. As we put this equal to 0, we will get a set of equations which we will have to solve for these parameters Qi. Okay, so this is the basic method that is followed in the Galerkin's method, Galerkin's approach. Yeah.
For the center point, value of E will be different. It will be minus P also. So for this was for the other points besides the center point.
You are talking of
The value of E you put in the integral W E dV.
the value of P.
E small e error.
P, that is the point load.
So E,
The value of E.
yeah, the error.
Okay, the value of E we are trying to evaluate at across this body. Okay, we are trying to evaluate this integral, this error at all the different locations,
Yeah.
and integrate that over the volume of the body. Okay, so the value of the error will be different at all locations.
This value d by dx of E times du by dx. So won't the P term will be subtracted from this for the center point? Because the way we have defined error, it's
You're talking of this term?
also in that integral
Where?
W E.
This step?
The main integral, yeah, which we equate to 0. Yeah.
Yeah, the first step.
Yeah, the error E.
Yeah,
So we have defined E as L of U minus P equal to 0.
yeah,
That means for the center point, the error will be this L of U, which is du by dx. D by dx of E times du by dx
yeah.
minus P.
Minus P.
And for the rest, it will be this.
For the rest, it will be that. That's right. Okay, because that point load P will be occurring only at the center point. In fact, that is why I said we have a discontinuity in the error function, and that is why we took it in a discontinuous manner to evaluate the integral. If you do it very rigorously, you will be able to get that.
That means we'll get the value of C1 to be different for the center point.
Value of C1.
Yeah, this. whole-
No, see what is C1? C1 is giving us the distribution we have assumed for U.
Yeah.
Okay, so C1 is a constant we have assumed. We assume that the deformation will follow this pattern. Okay, so the value of this C1 will not vary along the length of the body or along the volume of the body.
No, for the center point, if we do it with P also, the point load, so won't it come different?
No, that's exactly what we have done here. In this case,
We have already incorporated that.
yeah, we have already incorporated that in calculating these integrals.
Fine.
Okay, the error at the center might be different, but what we have to do is we have to integrate the error through over the volume of the body. Once we integrate that, only then we will get the value of C1.
So had it been like we have got at two different places we had point load, P at the first half,
Yeah, if you had a point load here and a point load here,
then we will do it in 4 steps
3 steps.
or 3 steps.
Because at the point load you have a discontinuity. What we will be doing now is that using this method, we will write down the general system of equations for a general 3-dimensional case. Okay, and then we won't have to do these steps in detail. Okay, we will get a uniform method which will be much more simple. All the complexities will go into the proof of that. Okay, so we'll take that up, and then maybe this confusion will not come. Okay, any other questions? Okay, what I will do now if you take a general 3-dimensional elastic material, okay, we said that for the elastic material, if you remember the equilibrium equation that I mentioned last time, those equations are of the form del sigma x by del x plus del tau xy by del y plus del tau xz by del z plus fx equal to 0. Okay, and so on. That's just 3 equations for this, 3 equations for the tractive forces, plus we'll have another 3 equations for point loads. Okay, if you take up those equations, we can incorporate all these equations into the Galerkin's approach in evaluating these integrals. Okay, let's just see how that can be done. Okay, for an elastic material, what we have to do is we have to find out the integral of W E dV. Okay, now this W will call that as phi. Okay, phi E into dV. In fact, in the book and other places also, this phi is the most standard notation for this weightage function. Okay, so the integral of phi times E into dV. If you want to evaluate this integral, this will look like del sigma x by del x plus del tau xy by del y plus del tau xz by del z plus fx, this thing multiplied by phi x, okay, plus we will have another such term multiplied by phi y, plus we will have a third such term multiplied by phi z, okay, and this complete thing multiplied by dv, this should be equal to 0. Okay, the second term would look like del tau xy by del x plus del sigma y by del y plus del tau yz by del z plus fy, and this would be del tau xz by del x plus del tau yz by del y plus del sigma z by del z plus fz. Okay, now these three give us the equilibrium equations for a general three dimensional case. This is the equation in the x direction. So this would give us the error term in x direction multiplied by phi x, that is the weightage we are giving in the x direction. Similarly, this term multiplied by phi y and this term multiplied by phi z. Okay, but this weightage phi that we are giving, that will consist of terms phi x, phi y, phi z. Okay, so this phi will be equal to this. Okay, and again in the Galerkin's approach we would follow the same method, the same constraints, that for u we will be assuming a certain field, we will assume a certain approximation for u. Okay, we will say u bar, let us say, is equal to u v w transpose. Whatever approximation or whatever formulation we choose for u bar, we will use the same formulation for phi, with the additional constraint that even for phi the same boundary conditions should be satisfied. Okay. Now the importance of satisfying the boundary conditions for phi, that we will be seeing later. Okay, well that ensures a particular type of condition for phi, we will come to that in the end. Okay, but if this phi is meeting this constraint and this u bar is the estimate of u, then this integral term we will try to put that equal to 0. Okay, and again in order to simplify this integral we will use the same formula that we had earlier, that is the divergence theorem. Okay, and this divergence theorem is what I wrote down over here. Okay, del alpha by del x times theta dv will be equal to minus of integral alpha del theta by del x dv plus n alpha alpha theta ds surface integral of that. Okay, so we will take this divergence theorem, apply it to this integral and then simplify the integral that we get. Okay, that will give us a simple method of applying the Galerkin's approach for all elastic materials. Okay. In the next class we will be using this divergence theorem to simplify this integral and continue from that point. Okay. So that is all we will be doing today.